Welcome to an exploration of ion transport in nanochannels, where the rules of classical physics break down and fascinating new behaviors emerge. At the nanoscale, ions experience a world fundamentally different from our everyday experience. Let's dive into this fascinating realm. First, let's understand what nanochannels are and why they're special. Nanochannels are tiny tubes or passages with diameters measured in nanometers, that's billionths of a meter. Here's a simplified view of a nanochannel. The diameter typically ranges from 1 to 100 nanometers. To put this in perspective, 1 nanometer equals 10 to the negative 9th meters. At this incredibly small scale, the properties of surfaces become far more important than the bulk properties we're used to in everyday life. Now let's understand a crucial concept: the electrical double layer. When a charged surface comes into contact with a solution containing ions, something interesting happens. Counterions of opposite charge are attracted to the surface, forming a layer. This creates what we call the electrical double layer, with a characteristic thickness called the Debye length. The Debye length is given by this formula, where epsilon is permittivity, Kb is Boltzmann constant, T is temperature, N0 is ion concentration, and E is elementary charge. Let's calculate the Debye length for a typical aqueous solution. Consider room temperature water with sodium chloride dissolved in it. Temperature is 298 Kelvin, and ion concentration is 1 millimolar, which equals 10 to the negative 3rd molar. The permittivity of water is about 80 times the vacuum permittivity. Converting concentration to ions per cubic meter gives us 6.02 times 10 to the 23 ions per cubic meter. Substituting all values into our Debye length formula, the result is approximately 9.6 nanometers. This is the characteristic thickness of the double layer. When the channel diameter is comparable to or smaller than this Debye length, surface charge effects completely dominate ion transport. Let's understand what happens when channels become this small. In a large channel where diameter is much greater than Debye length, ions move freely in the bulk, and surface effects are negligible. But in a nanochannel where diameter is comparable to Debye length, the double layers from opposite walls overlap, and surface charge controls everything. This overlap creates remarkable selectivity for certain ions. A nanochannel with negative surface charge will preferentially conduct positively charged cations. Cations are attracted to the negative walls and flow easily through the channel, creating high conductance. But anions, having the same charge as the walls, are strongly repelled and cannot easily enter or pass through the channel. The selectivity ratio, defined as cation current over anion current, becomes much greater than 1. Now let's explore ionic rectification, one of the most fascinating phenomena in nanochannels. Ionic rectification means that current flows much more easily in one direction than the opposite direction. Under forward bias with positive voltage applied, cations flow easily through the channel, producing high current. But under reverse bias, with negative voltage, ion transport is strongly suppressed, producing much lower current. The rectification ratio is defined as the forward current divided by the reverse current. Let's use an intuitive analogy to understand this behavior. Imagine walking through a hallway where the walls are covered with sticky magnets. If you carry an object with magnetic polarity that's attracted to the walls, you'll move easily in one direction. But if you try to go the opposite direction, or change the polarity, the magnets strongly resist your movement. In a large, wide hallway, the walls don't affect your movement much because you can stay in the center. But in a very narrow hallway, you're constantly interacting with the walls, and their properties completely dominate your experience. Let's estimate the rectification ratio with a simple calculation. Assume our nanochannel has a fixed negative surface charge density. Surface charge density is negative 10 millicoulombs per square meter, and channel diameter is 10 nanometers. The surface potential is approximately sigma times d over 2 epsilon. This gives us a surface potential of approximately negative 70 millivolts. At room temperature, the dimensionless potential E psi 0 over kBt is about negative 2.7. This means Kphi concentration near the surface is enhanced by an exponential factor. The factor is e to the 2.7, which equals approximately 15. This leads to rectification ratios that can easily reach 10 to 100 or even higher in optimized systems. Another fascinating phenomenon is nonlinear ionic conduction. In classical systems, we expect Ohm's law. Current is proportional to voltage, giving a straight line. But in nanochannels, we see strong nonlinearity, with different slopes for forward and reverse bias, demonstrating rectification. The current-voltage relationship becomes exponential, similar to semiconductor diodes. Let's understand why our usual continuum description fails. The classical continuum view assumes that bulk properties dominate, and surfaces are just boundaries. Volume scales as diameter cubed, while surface area scales as diameter squared. So the surface-to-volume ratio scales inversely with diameter. At the nanoscale, surface area becomes so large relative to volume that surface effects dominate everything. At the macro scale, the bulk volume dominates, and surface effects are negligible. At the nanoscale, the surface dominates, and bulk properties become secondary. Surface charge creates distinct zones of ion depletion and accumulation. When nanochannels selectively transport certain ions, they create concentration gradients at the entrance and exit. Near the negative surface, we have an accumulation zone rich in cations, followed by a transition zone, and finally the bulk region. Cation concentration follows a Boltzmann distribution that depends exponentially on the local electric potential. These phenomena have important practical applications. Nanochannels with surface charge can selectively remove ions for desalination and water purification. The rectification behavior enables ionic logic circuits and highly sensitive biosensors. Selective ion transport can be used to harvest energy from salinity gradients between fresh and salt water. In energy harvesting, the salinity gradient drives selective ion flow through nanochannels, generating electrical current. Let's compare the relevant length scales to understand when these effects matter. The Debye length typically falls between 1 and 100 nanometers, depending on ionic strength. When channel diameter is in this range, surface effects dominate. Another important effect is concentration polarization at channel entrances. When nanochannels selectively transport certain ions, they create concentration gradients at the entrance and exit. Cations accumulate on one side and deplete on the other, creating a concentration polarization effect that can limit transport. The limiting current is proportional to the diffusion coefficient times concentration difference, divided by the boundary layer thickness. Temperature plays a crucial role in nanochannel ion transport. The Debye length increases with the square root of temperature. Higher temperature increases thermal energy, which competes with electrostatic interactions. At room temperature, thermal energy kBT equals 25.7 millielectron volts. For significant rectification, electrostatic energy must be comparable to or larger than thermal energy. Nature has been using these principles for billions of years. Biological ion channels in cell membranes are essentially nature's nanochannels with diameters of 0.5 to 2 nanometers. A protein ion channel spans the cell membrane, creating a selective pathway for specific ions. Biological channels exhibit all the same behaviors: ion selectivity, gating, and rectification. They can be highly selective, allowing only specific ions to pass through while rejecting others. They can be gated, meaning they have mechanisms to open or close, controlling the flow of ions through the channel. And they can rectify, allowing ions to flow more easily in one direction than the other, similar to our nanochannels. These properties are essential for various cellular functions, including maintaining proper ion balances and generating action potentials in neurons and muscle cells.